Now, the next talk, that's by Peter, Under the Hood of a CPU, Reverse Engineering the Intel P6 Microcode. Peter Bosch, who is a university student at Leiden in the Netherlands, he would deep dive into the mask ROM extraction, IC reverse engineering, and reconstructing an undocumented instruction set. So Peter, over to you.
Right, welcome. Just turn on screen sharing so we can see the slide. Yeah. Okay, can you guys all see my my title slide there?
Yes, now we can see it.
Right, okay, so let's go. So, yeah. Okay, so I'm a student of computer science and physics at Leiden University. In the past, I've written an emulator for the Intel Management Engine. And together with Trammell Hudson, I found a checked and views vulnerability in Intel Bootguard on the SPI bus. You can find me on Twitter or write me an email. Right, so let's start. So on modern x86 processors, at least from Intel, the native instruction set that the thing actually executes is not really x86. It all translates it before running it. So you can imagine a x86 instruction is kind of complicated to deal with because of different addressing modes, and there's not really a clear encoding to all the fields. It varies per instruction. So it all translates it into a more RISC-like instruction set. There's actually been some arguments about whether or not you could call it RISC, but it really isn't a normal microcode. So normal microcode would usually say, like, connect this execution unit to that bus or something. This is actually more normal instructions with an opcode and regular form. So if you have a simple instruction, it'll map onto one microinstruction. If you have a more complicated one, might be 2 or 3 or 4. But then if you look at the really interesting ones, like, for example, write in Azar, you might see this in this listing that Intel publishes. You'll see it's complex. So what does that mean? It actually invokes a full subroutine within microcode that's even able to do control flow within itself. It's a real program that will do all kinds of things like edit internal control registers or perform some check before doing it, or even extract an update. So, you know, what if you want to see what goes on here? Maybe for security research, maybe if we're just interested in it. Well, usually if you want to look at the firmware for something you don't know, you first see, hey, is there an update that we can find that we can extract? So, and then you go maybe on Wikipedia and you see, is there any info on it? It says, oh yeah, there's an update format. And it lists a bit how big it is and everything, but then it also goes on and says, there's 2 layers of encryptions and they're explicitly not documented internally. Apparently only being known to less than 10 employees. I think that's a bit of an exaggeration, but whatever, not going to be easy to extract it. Right, maybe get it from a running system. Okay, so there's these test ports that you can access over JTAG, and you can actually read at least the patch RAM, so the decrypted update. But they're all locked. You need to authenticate with at least on a modern CPU, with a long key that you get from Intel servers after sending like the unique serial number. And I've done the math, it's not feasible to actually go and brute force this, unfortunately. I've looked into maybe glitching it open, haven't made it work yet, but that's all different folks, I think, if I ever get it working. Someone else did actually manage it on an Atom, because that's one chip with the Southbridge and has the management engine on the same chip. And actually, if you unlock the management engine through a vulnerability in its operating system, you'll be able to access the test port on the CPU and get the microcode out. But that's on an Atom, which, as far as I know, is not really related to modern CPUs, because it's a separate architecture, microarchitecture. P6 actually, that's the Pentium Pro, Pentium II, is the earliest ancestor of the modern Intel core microarchitecture like Skylake. And I've seen some source level microcode for Skylake, which was actually like accidentally put on GitHub by Intel. It's very similar to what's described in the P6 patent. So, you know, last option is getting it out of the mask ROM. I think John McMaster already talked a bit about this. It's kind of complicated. So I didn't have to delayer the chip for this because I actually found someone on Flickr of all places who's got really nice deprocessed die shots up there of a Pentium II. And you can actually already see the microcode ROM on there. It's the area marked MS. So yeah, I just went out on a limb and asked the guy like, hey, can you do a higher resolution scan of that? Because you've already got the deprocessed chip. You know, yeah, he actually was willing to do that. And he first ended up sending me some of the other arrays because they're smaller before committing to doing the large microcode one. So, you know, yeah, I got that and I looked at it a bit closer and you can already see, even in that like kind of zoomed out photo, that there's clearly data there, right? See like the pattern here. I've annotated the different arrays that are part of the ROM, but you can really clearly see there's data. So first try. Tried Adam Laurie's ROMPAR tool. I think it's Adam Laurie's. So this thing actually does basically does brightness thresholding, and yeah, I was thinking, okay, this is working kind of well, but it's also not really a user-friendly tool to use. And I got some better photos, and I looked at it closely, and I discovered, okay, that's never going to work because actually two cells on neighboring rows share a drain contact. And so they look like a bridge if both of them are set, or like a tab if only one is set. So brightness thresholding on at least photos of this resolution is going to be incredibly tricky and error-prone. So this is the structure of that ROM cell. I hope everything's right. I'm not an electrical engineer. But yeah, basically what you're seeing actually, because this chip has been fully etched to silicon, there's nothing left on there except for the substrate, is like the kind of height differences left by the threshold side. So on a modern fast chip, they will actually etch kind of ditches between the transistors to prevent them from having crosstalk on each other, I think. And that's what you're seeing, basically just a height difference, which is also why the contrast is so low. So the way I've done it, actually, I've set there's 4 different kind of cells, kind of, you know, bottom row set, top row set, or both set, or none. And if you're looking at these, you know, it's not really a great signal to noise ratio here, right? So what I ended up coming up with for getting this out is basically just crop the cells, and like, you know, every good computer science problem, preprocessing can solve a lot of your problems. So you can see that most of the structure is actually in the vertical direction. So I've averaged it along, saying the y-axis there, and the x-axis. So just basically flatten it in the direction it does not have a lot of information, and you get a 1D function that's a lot easier to work with and has less noise because you've got, you know, the noise cancels out and information adds up if you average. So then what I do is I just use some statistics 101 trick, basically just least squares fit method. I have reference functions for the four different kind of cells that I recognize, and I have the unknown cell, and I compute the score using this function for all of them, and I just take the one with the lowest, that's the best score. And this is really simple, and I wasn't expecting it to work very well, but you know, I built it first in a like kind of Python notebook, and it worked really well, and built an application around it, which is actually now has a lot of features. Spent way too much time on this. I wrote the first version in a week, about right just after COVID started. Didn't really have a lot to do. So yeah, it's called PLA decode because, as you'll see later, I first started looking at PLAs and not at the ROM itself. But it also does ROMs. They're basically just a special case that doesn't use a lot of the functions. It'll even generate C source code for a PLA that you've captured in it. It has a Qt UI that has one big improvement over ROMPAR, in my opinion, and that's that almost all of the like internal state and everything is accessible through the right pane. So you don't ever have to go back and undo something really, because you can just, like, you know, if you just click the bit wrong, you can correct it again. It also allows confirming values that you've read out. So for the ROM, I actually like to go and check every cell manually, and then I'll just click a row like, okay, this is okay, and it'll annotate that. So that's kind of the tool I've been using for this. Okay, and then I've done that on the whole array, and I get this. Yeah, there's clearly some structure there. And you can see there's everything seems to be in patterns of 4 wide. It's a bit difficult to tell here, but yeah. And then there's also seems to be 3 copies in like the first bit. So the top one is the left array of the ROM, and the right one is the right array of the same block. So the right one seems a lot more complicated, hard to find a pattern there. The left one's pretty clear. Just for reference, these are the 2 arrays, and there's also small ones in the middle. We'll be looking at them later. So now to decode it. First of all, what's in those microinstructions, right? So there's a patent, and it shows this. Like, it should have some control bits, an opcode, source, destination, maybe immediate. Okay, so it's all pretty clear. Right, and then the same patent actually also has this diagram, which is a block diagram of the decoder, the thing that turns x86 into microcode that's then thrown into the processor. So yeah, you've got like 3 micro ops coming out of the ROM. It says 80 bits here, but this is actually from a development version of the architecture. The real chips all use 72 bits. But yeah, there are basically 3 micro instructions coming out of it per clock. So probably also 3 on a row. And there's also these things, translation PLAs, which are just programmable logic arrays and the NOR planes that take x86 opcode and turn them directly into microcode, which is why you had like the distinction between 1 to 4 micro ops and complex. So that's actually really nice. At this point, I just stopped looking at the ROM for now. I just thought, if I can figure out these PLAs, I basically have like, you know, Rosetta Stone from archaeology, where you had 2 languages or 3 even on a big slab of stone next to each other with the same meaning. One of them you know, and then you can figure out what the other 2 do. Well, same here. You put in known x86 instructions, and then you get microcode out. So looking at these, basically you've got a NOR plane at top and an end plane at the bottom. This is not actually a translation one. This is the entry point, which has the same structure, but it's smaller, so it fits on screen better. Just use my tool again. And then I noticed this. The OR plane actually seems to have a slight difference between some of the positions. Like this one has kind of a hook to the left, or to the, like below, and then this one has it on top. So there seems to be a bit more structure than what I'm currently looking for. So yeah, and basically, like, what's that structure doing? Seems like there are 2 readout lines per row. How do I tackle this? I realized I had to look at the metal layers at least, or at the active layer. So what I didn't want to work with hydrofluoric because I'm pretty scared of the stuff. So I decided using brass polish to just slowly manually polish off layers of the chip. And this really doesn't give you good tonality, of course, but for a small area of interest, it works fine. Is a lot of effort, but yeah. Also built my own microscope. I'm kind of planning to maybe talk about that some other time, but yeah, and also did dare to use some chemicals like aluminum etch, which is mostly phosphoric acid, and also some potassium hydroxide to just strip some of the really thick glass layers. I had to mask up the silicon because it etched silicon faster than glass actually. But yeah, so I started looking at the actual readout circuitry to figure out what is that extra readout line per thing doing, because it had exactly 72 rows in the OR plane. So I was thinking, you know, yeah, this has got to be the right amount of data, but then why does every one of those rows have 2 readouts? So I look at this, trace it all out into SVG first. A lot of work. With small area of that. And this is the whole thing in Preregister. Looks really complicated, but once I figured it out, basically just a NAND gate, and it's all negative logic, right? So basically OR. And some pre-charge logic and a weak latch to like prevent the line from changing states in the middle of the clock cycle, I think. But yeah, basically those two lines are just OR together. Also, the PLA actually is full into kind of, and those are OR together as well. So right. Then, you know, I've got this and I can start looking at the output of them because I can generate C source code using my program. So basically just feeding it some instructions with known semantics, exchange, switch to the contents of two registers. So like every programmer knows, you need to do about what it says on the right. Temporary registers A is B, B gets set to T, 10, right? So looking at what it produces, one of the four micro instructions that it generates seems to be kind of random. So it makes sense. If we looked at the table, it said it had only 3 micro instructions. So I guess that's just what's it called, like no care output for the PLA. And the other one seemed to have this pattern, which is just like what I wrote on the right. So probably source and destination fields, or the other way around maybe, and maybe the thing in the middle is the other source. Okay, so, and then we can also look at instructions that should be similar but not the same, like for example, push CS, push SS, ES, etc. And this allowed me to find where the logical segment for the micro is stored. Okay, so now I'm getting somewhere. I know this makes sense. I know I'm able to work out the encoding. So let's get back to the ROM. So there's 924 ROMs in a physical row, for columns in a physical row of the ROM. And there's a 72-bit microinstruction word. So that's a bit too large. Well, we figured there were 3 in them. So it's still like 1 or 2 orders of magnitude larger than what it should be. Okay, so already noticed a pattern of 4 columns having kind of the same handling weight just by looking at the bitmap of it. That due to row interleaving. So they're stuffing 4 logical rows or addresses even into one physical row by just first putting all the first bits of one and then etc. You know. So that was easy to undo, but then it still looked pretty chaotic. How am I going to map this onto those 72-bit micro instructions? For the left hand, I thought let's just take like the third, but the right hand didn't seem to have any such pattern. And I looked at the chip again using my microscope setup, and I found this lovely bit between the PLAs and the muxes and the ROM. So the bus leading up to the right here is, oh, this goes to the multiplexers that switch between the translation PLAs and ROM. And this goes up to the ROM. Well, you know, there's no real good reason to do this. I think it's just to slow reverse engineering or something, but they're scrambling all the bits. So I had to figure out where every one of these traces went and what the mapping was. So I ended up tracing the whole relevant bit of the circuitry in Inkscape. It took me way too long, but in the end I got it. And you've got, like, here are the arrays for the microcode ROM. So this is just looking at metal, not active layer. Here's the readout circuit. That bus, the weird, annoying bit. And here's the PLAs. And one of them, like, there's only 3 microinstructions per cycle coming out of the ROM and 4 from the PLA. So you can see like 1, 2, 3, and here would be the 4th, but it's not connected to it. And here would be the multiplexers. So I manually annotated the start and the ends of the traces, like these as being the column numbers and that as being the micro instruction bits. I just assumed, by the way, that the PLAs were in logical order. which they seem to be from my earlier results, right? And this again is that weird stuff in the middle where it's just scrambling it all. Right. Also a close-up of the readout circuits. All the red boxes are basically like kind of like logic cells that do latch the output of the ROM and put it on the bus. Wrote a Python script to actually determine connectivity from this, and I ended up with a table on the right. So there's definitely some patterns here, but yeah. So the left column here, this is the column number in the right array. X means first micro-op Y, second Z, third, and then numbers after it is the bit in the micro instruction. The red one was one that at the time I took the screenshot hadn't found out yet, but basically, yeah, I was right to trace this out from the chip because it's just non-trivial, this mapping. In meanwhile, I was also just Googling around a bit more, and I found this thing. Remember when I showed you the table of the number of microinstructions per macroinstruction? Well, I'd already heard from some people that in the really early days, the developers at Intel wanted to give the microcode out to compiler writers, but I didn't think it ever happened. Then I found this pre-release version, I think, of the same document. It was on Google, but it did have confidential markers on it, but it was just sitting at 4 different places, just right in Google results. And it actually lists the source code for the microinstruction generated from the translation PLA. It's not complete. It doesn't, like for some of the micro-ops, it doesn't actually show the opcode or mnemonic. But yeah, so I went back to the PLAs and I looked, for example, at the set direction bit for macro instruction. And the bit here is copied from that document and it has immediate mode values in it. Why does it have the immediate mode values in a document that's just supposed to show pseudocode? You know, I'm glad they did. And oh, what do you know? Output from the PLAs has the same value at these bit positions. Again, like nicely aligned to a nibble even, so I can see it in hex without having to compare the binary representation. So I found the immediate field. So now I kind of know what the encoding is like, figured out some other fields as well. You've got your obvious things, right? Source, destination, immediate. There's also some other stuff. Alias, another alias, and flow marker. Flow marker is for sequencing. It basically denotes the first and last micro instruction belonging to a macro instruction flow. There's also some other things marked in there, but I really haven't figured that out yet. Right. So what instructions are there? From the one micro op for some macro instructions, we know there's just a lot of them that correspond to the instructions in the x86, the simple instructions in the x86 instruction set. Don't know their encoding yet. So I went looking at patents again, and I found this thing. And it actually, for some micro instructions, it doesn't list the entire encoding, but it does actually describe the semantics. It even has pseudocode for some of the micro instructions, which seems like something you'd find in their internal like micro ISA documentation, but not in a patent. It's not even written like a patent. Like no weird in one embodiment stuff. It's just clear technical literature. So okay, the rest of the opcodes you just had to figure out by looking at a lot of generated stuff from PLAs. But this was nice to at least know what was out there. Let's see. So the immediate operands are a bit more complicated than you might expect from a normal instruction set. There's 2 fields that control this. Actually 3. In one of the source fields, you actually put constant instead of register. And then there's an immediate field and immediate alias field. The alias field actually selects what kind of value is used. So you can't only use the actual immediate 9 bits from the micro instruction. But if you need a 32, like it can also do a lot more. If you need a 32-bit immediate, there's actually a constant ROM that you can index. You can take one of the values generated from the macro instruction. You can also select stuff that already has the instruction pointer added to it for branches. So you really have to look at that alias field and the immediate field, because if you select the macro instruction, it will use the immediate field to index what register you want. And that's all described here, basically. So I haven't figured out all of this. Also, the constant ROM, I've looked at the kind of bird's eye view die shots a lot. I haven't been able to identify an area that is likely to be the constant ROM. So that's definitely something I need to find. But a lot of the important constants to at least get an idea of what's going on are encoded directly. So the register values, so the microcode, I didn't mention this before, but the microcode is still before the out of order engine. So it's not renamed yet. It uses logical register names, not the physical reorder buffer entries. So these are the encodings for that. And you've got all your like x86 registers, right? Even the different sizes. There's also some ones that some encodings that I haven't understood. But there's temporary registers. There's probably some more somewhere, because patents again say there's 12 temporary registers, not 6. And yeah, these are just used by microcode to avoid having to trash one of the architectural registers. And then there's some special encodings that allows the macro instruction to select a register or a size. I think the duplicate of the general registers here is just the size being taken from the macro instruction. And the other ones take the actual register from the mod_rn byte or from the opcode itself. It also encodes segments directly. And what's interesting here is that there's way more different segments than are architecturally visible. There's, of course, your normal x86 segments, but it also treats the GTR, IDTR, and LDTR as segments, as well as the task register. And there should also be a lin seg and a phi seg, which allow direct linear and physical address loads and stores. And then control registers. So here's a bit of that Canon Lake microcode that was on GitHub for a bit. Control registers are not actually registers, like architectural registers, so to speak. They're on a different address based bus. So there's move to and move from control register micro ops. I guess you can compare it to like the IO ports in x86, but this is internal. So if you do write MSR, it's really more like an IO CTL, and you are invoking a subroutine based on the name of like the address of the MSR. Some of them map one-to-one on an internal control register. Other ones like invoke a very different, very complicated program like the microcode update one does. What's on the screen here is funny. It's actually this is the fix for the memory sinkhole vulnerability that Christopher Domas found. So just checking the value you put into the epic-based register. But yeah, that's also where I got a lot of the mnemonics and everything from, because even though the encodings are different, that was very similar in at least the mnemonics to all the patents I saw. So I just assumed it's kind of the same thing but newer. Right, so let's just look at some example microcode. Divide instruction. This one's funny because the Pentium II, it's really old, right? So it's 32-bit processor, you'd say. Well, internally, because actually the first execution unit is shared between floating point and integer, all of the the common data bus in your out of order engine is actually I think 86 bits wide. Even has some flags on it for floating point stuff plus flags. And it uses this for integer things too. If you're doing a divide, it takes a 64-bit operand, right? An x86 divide instruction, EDX, EAX. First thing it does is, let's just turn this into a single 64-bit value and continue our computation with that. So here is your mid-90s 32-bit microprocessor internally, just working on 64-bit values just fine. And then it's taking it apart again, right? It's moving the 64-bit register into a 32-bit one, and also using a separate micro op to get out the high 32 bits. And now for something more complicated. I don't know if anyone recognizes what's going on here. Doing a lot of loads, restoring all the general purpose registers. I'm not actually able to see the chat well. And so the segment register. First, I thought this is like task glitch or something, like hardware task glitching, which used to be a thing in 32-bit x86. But no, it's even more interesting. It's the system management mode resume instruction. So I definitely have to look more into this because I know it's also going to be setting a lot of the control register. And then another nice one is this. This is part of one of the IO port instructions. And here it is actually loading offset 66 of the task state segment, which is the base of the IO privilege bitmap. On x86, you can basically override the security checks and say, right now we're in user mode, but you're allowed to access some IO ports using a bitmap. Here it's just reading that. And you can really recognize these features of the x86 architecture in microcode here. So we know it's like, we haven't got it all figured out yet, but it's kind of, it's getting there, and we're like, these are definitely sensible instruction flows for the behavior we know the architecture to have. So last one I want to show is this. This is the reset vector. It's just initializing part of it. It's initializing all the general purpose registers. Most of it's 0, but then here it is loading some control register into EDX and ORing it with 660 hex. This is from a Pentium II Dixon. It just happens to be family 6, model 6, and EDX is supposed to be the model family stepping CPU ID on reset. So yeah, this was one of the first things I recognized in there, and I knew, yeah, I was on for something. So it's far from done. There's a lot that still needs to happen. I still need to finish converting all the images to bits. I've done it for about half the ROM, but it takes me about a day per block, because I want to convert it manually, because I haven't figured out the entire encoding, and I really don't want to deal with bit errors I don't know about. I need to figure out the rest of the opcodes and registers. It's probably going to take a while. And there is actually one bit of the microinstruction that I haven't managed to map onto the ROM. So the 6 bits, so the 64 of the micro opcode are not actually correctly extracted right now, but most micro ops do not have that sense, even in, like, at least in the PLA. So I guess most of the output's fine. I need to find the constant ROM. And I really want to figure out how the updates work, right? Because if I know that, I know the Pentium, like the P6 CPUs, not to have any kind of asymmetric validation. It's just symmetric crypto going on. So if I know what the encryption is, I can load my own microcode updates. I can access the control registers, and through that, hopefully extract the microcode in software and get a bit perfect copy. So that would all be really interesting. Also, of course, like being able to mess around with microcodes would be really cool. Also, I haven't figured out the entry point PLA yet, how the input to that works. Right. Then there's just some people I'd like to thank for all this work. Martijn Boer, who is the guy on Flickr who actually got me the scans that I need. Yeah, I just basically wrote an email said, hey, you've got this chippy process, you seem to have a microscope. Could you please, for this project, scan this? And he's like, yeah, sure, sounds interesting, don't do that. Also my hackerspace, because it's just a really good place to hang out and to work on things that would be very difficult to do at home. Then there's someone at a hackerspace, NoPavel, who just kept taunting me like, hey, you know, like, it would be cool to see microcode. And I had this idea for a while, but I never really wanted to get started on it because I thought it was just going to be impossible or something. That kind of got me over the threshold of actually starting to try it. And then there's Peter Sawinski, who just kept scrolling through the auction sites and finding ridiculously good deals for microscopes for me to buy to improve my setup with. Like the thing I built on my own wasn't exactly good enough to work on this 250 nanometer chip down to like the active layer. I could get all the metal layers, but the active layer was proving too difficult. So yeah, and there's a lot of other people as well that helped along the way. There's a guy at Hackspace who lent me a microscope to get started before I bought my own, etc. Right. So anyone have any questions?
Thank you, Peter. There are a few questions, and let's take them. Let's take two questions, and then we can open the breakout room. So
right.
Let me read the question for you, if that's okay. Or you
Yeah.
want to scroll through the chat?
No, you can read them to me.
All right. Why do you think the scrambling is for anti-RE as opposed to signal integrity?
It could be for signal integrity, but like I said, I'm not an electrical engineer, but I don't really see any reason because maybe they actually like did some statistical analysis on the Hamming weight of the different positions, but they're all like signal types, right? They're all part of the instruction. There's no ground lines between there. So might be, I don't know. And they could have done it. So the weird thing is like 50% of that bus, it's not happening. And those lines are also parallel. So it doesn't make a lot of sense to me. Right. So what was the other question?
Okay. We just got one. I'll take that one. How much of this RE process do you think could be performed on more modern CPUs?
Well, so the actual capture part of it is going to be a lot more difficult. You're going to require something like a scanning electron microscope or something like that. I've also heard they're doing some hardware compression on the Microcode store. At least they have patents on it. I don't know if they're actually doing it. But at least for Sandy Bridge, the microinstruction is 78 bits, I think. And it seems to have roughly the same structure. So if you could get it extracted, then a lot of this could be used for that. Yeah, so it should be possible if you have the tools.
All right, Peter, thank you so much for this amazing presentation.